B viscous viscous forces or viscous force term. So before deriving the viscous force terms, let's first build some physical intuition. So to understand viscosity and the motion of a Newton fluid, we're going to consider a simple and classical configuration, planar quad flow. So we consider a fluid confined between two infinite parallel plates. The top plate moves at a constant velocity. Sorry. The top plate moves at a constant velocity v, and here v is called u is the component of the velocity in the x direction, and v in the y direction, and w in the z direction. So the top plate moves at a constant velocity and the bottom plate is fixed. Bottom plate is fixed. So due to the plate moves in the y direction, but it varies along z. So due to no slip condition, the fluid particles in contact with each plate have the same velocity as the plate. As a result, the fluid is dragged by the moving plate, and the velocity varies continuously. So this creates a velocity gradient this creates a velocity gradient, and the profile velocity is linear. Therefore, we can say viscosity is a measure of the resistance of a fluid to velocity gradients. So, viscosity is associated with shear stress, which is a force per unit surface area, like pressure. However, unlike pressure, viscosity or viscous force act tangentially to the surface. So we can say we see the tau, which is the shear stress, is defined as a force per unit surface area. So that means the viscous force of equals tau times the surface. So you can write tau, and shear stress is proportional to the gradient velocity. So tau y z equals mu partial v over partial z. V is the component of the velocity in the y directions. So yeah, mu is the dynamic viscosity. Dynamic viscosity. So we keep working with the same fluid element, the same cube. There is another force on the bottom face, which is opposite to the force on the top face. So on the top face at z plus delta z, the viscous force is delta F sub V. The top face equals mu partial V over partial Z evaluated in X, Y, Z plus delta Z, Z plus delta Z times delta X, delta Y. And at the bottom face at Z, the viscous force delta FV bottom face equals, so on the bottom face this force is opposite to the y-axis. Then there was minus sign here, minus mu partial V over partial Z evaluated in X, Y, and Z, delta X, delta Y. So the net force is the sum of the two contributions. So delta F sub V Y equals delta F sub V top plus delta f sub v bottom, which is mu partial v over partial z evaluated in x, y, z plus delta z minus mu partial v over partial z evaluated in x, y, and z. Delta x, delta y. So we now expand the velocity gradient using a Taylor expansion. Partial v over partial z evaluated in x, y, z plus delta z equals partial v over partial z evaluated in x, y, z plus partial over partial z partial v over partial z times delta z. So substituting in the net force expression, we get delta f sub v y equals partial v over partial z written x, y, z plus partial squared v over partial z squared delta z minus partial v over partial z sorry, partial v over partial z, where it is x, y, z, mu delta x delta y. So which is partial squared v over partial z squared times delta x delta y delta z. So the net force per unit volume is F V Y equals delta F V Y over delta V, which is mu partial square V over partial Z squared over partial Z squared. Sorry. Partial Z squared. So this shows that the viscous force depends on the velocity gradient, which naturally leads to a second derivative of the velocity. And in full three dimensions, the viscous force is F equals mu Laplace squared V, which is also mu operation